Hello, good morning. Today's discussion will be on the collision between two particles. We shall apply the law of conservation of momentum, kinetic energies, etc. in the case of colliding particles, and we shall see how we obtain the final velocities of colliding particles if we have a knowledge of the initial velocities. Okay. Now, when you say collision, it is not necessary that the colliding particles have a physical contact. Okay, collision just refers to a mutual interaction between the two particles, such that as a result of the interaction, their motion is affected or their path is changed and their momentum is changed. So collision is just a mutual interaction between the colliding particles. Collision means, you can define collision as a mutual interaction between two particles, as a consequence of which their path is affected and their momentum can change, or their motion is affected. For example, if you are considering the collision, if an electron is incident towards an atom, it will be affected by the electrostatic Coulomb force and may cause a deviation in the path of the electron. So it is not necessary that the two particles come into physical contact for a collision to occur. So let us consider here, for example, two particles of masses m1 and m2. We have two particles of masses m1 and m2. Let their initial velocities be u1 and u2. Initial velocities we are taking as u1 and u2. Okay. So these are the masses of the particles and these are the initial velocities of the particles. So let after collision, let the final velocities of the particles be v1 and v2. So according to the law of conservation of linear momentum, you can write m1 u1, velocities are vectors, okay, plus m2 u2 is equal to m1 v1 plus m2 v2. This equation is nothing but the law of conservation of linear momentum, which states according to which the total momentum before collision will be equal to the total momentum after collision. Okay, law of conservation of linear momentum. Now, when you say before collision and after collision, you can say that the position of the particles will be well separated. Okay, so that the interaction before and after collision, the position of the particles, distance between the particles will be larger. The position of the particles will be well separated, so that the interaction is almost zero. The interactive force between them is almost zero. In that case, the potential energy of the particles remain constant before and after collision. So let us see what happens to the kinetic energy. Okay, so the total initial kinetic energy can be given as half m1 u1 square plus half m2 u2 square. After collision, naturally, you can say that the kinetic energy is half m1 v1 square plus half m2 v2 square, right? So there are collisions in which the total initial kinetic energy is equal to total final kinetic energy. So such collisions are known as elastic collisions. So in the case of elastic collisions, the total initial kinetic energy. So what will be the total initial kinetic energy here? Half m1 u1 square plus half m2 u2 square is equal to total final kinetic energy, that is half m1 v1 square is plus half m2 v2 square. So in elastic collision, total, or you can say that kinetic energy initial equal to kinetic energy final, that is the kinetic energy will be conserved in such type of collisions. Okay, this momentum here, this is initial momentum. Momentum initial equal to momentum final. according to law of conservation of linear momentum. So in all collisions, any type of collision you may take, the total momentum of the colliding particles, sum of the momenta of the colliding particles before collision will be equal to the sum of the moment of the particles after collision. Whereas kinetic, it is not necessary that kinetic energy is conserved in all the collisions. Okay, so in certain collisions kinetic energy will be conserved. Such collisions are known as elastic collisions. In certain other collisions the kinetic energy may not be conserved, and such type of collisions are known as inelastic collisions. Okay, so usually if you have a gas collision of gas molecules, if the kinetic energy of the molecules are conserved before and after collision, if the kinetic energy remains the same, then you can say that it is elastic collision. In the case of inelastic collision, what is happening? Where does the kinetic energy go, or what can happen so that the kinetic energy is not remaining conserved? So you can consider a collision wherein initially the atoms or molecules whichever are colliding are in an excited state, and after collision this energy may be getting converted into that kinetic energy. So in such cases the total initial kinetic energy may not be equal to the total final kinetic energy. So there you can write the equation as half m1 u1 square plus half m2 u2 square plus E is equal to half m1 v1 square plus half m2 v2 square. Okay, so here in this case the final kinetic energy will be slightly greater than the initial kinetic energy. Also there may be situations wherein initially the colliding atoms or molecules are in lower energy state. After collision they gain they get excited, that is there will be a change in their internal energy or internal structure, and as a result of which they are getting excited. In that case their final kinetic energy may be slightly less than the initial kinetic energy. So in such cases you can write the equation as half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square plus E. Okay, so both these cases are inelastic collisions, because here total initial kinetic energy will not be equal to the total final kinetic energy. So basic knowledge of the initial velocities of the particles and the law of conservation of momentum and kinetic energy is not sufficient to find out the final velocities of the particles, because when you have two colliding particles, you have the final velocities v1 and v2. If you are taking general 3 dimension, you need 6 different equations, equations to solve, because v1 will have 3 components, v2 will have 3 components, so you need 6 set of equations to solve for the final velocity. So here you can have 3 sets of equations using the law of conservation of momentum if we write in the component form, and one equation either if you are taking this or these cases, you have only one equation relating the velocities. Okay, so you have only in effect 4 equations, but you need 6 equations to find out v1 and v2 in a general 3-dimensional case. But that is, you can find out the final velocity of one particle only if the final velocity of one of the particles is known and the initial velocities are known.